For postulate 4, we have if a system is described by a wave function psi, then the average value of the property A, whatever physical observable A refers to, is given by the expectation value of A, which is equal to the integral over the entire domain of the wave function. If this is one-dimensional x, this is from x equals minus infinity to infinity. If it's three-dimensional, it's minus infinity to infinity in all three Cartesian directions, etc. It's integrate over the entire domain of the function psi. And this is psi star, complex conjugate of psi, the wave function, times the operator A, so the operator for the corresponding classical observable quantity A, and that operator acts on the wave function psi. And again, that's integrated with respect to some volume element depending on what the domain of the wave function is. So this whole integral then divided by, if the wave function is not normalized, we need this integral, which is just integrating the wave function times its complex conjugate over that same entire domain of the function. So if we have the normalization condition met, then we would have the integral from minus infinity to infinity of psi star psi d tau, whatever volume element we're talking about. We would have that equals 1 if psi is normalized. So this way of writing it normalized, still very bad. Okay, normalized. So this way of writing it on the left here is the most general way of writing it. You don't have to have a normalized wave function necessarily, but if we do have a normalized wave function, then we can just make the simplification and say that the expectation value of A equals just the numerator, which is integrating over the domain of the function psi star operator A acting on the wave function integrated over the volume element d tau. Okay, so for a specific case, like what we talked about in the previous video, if the wave function is an eigenfunction of the given operator A. So let's say if psi equals psi n, the nth eigenfunction of operator A, so an eigenfunction of operator A, then what we have is, in order to calculate the expectation value of A, we have, and let's also pretend that it's normalized as well, so we're just going to do the top part. We would have the integral from minus infinity to infinity psi star A psi n d tau. But for when we have an eigenfunction, then we know that the following criterion is met. We know that the operator A acting on psi n equals a constant a n, the nth eigenvalue operating, times that nth eigenfunction again, that you get this type of a result. So going back to the bottom, this part here with the operator acting on the wave function is just the left side of this equation. So we can continue that on by making that psi n star stays the same. But now we have a n psi n d tau. Now this a n, by definition, this being an eigenvalue equation here, is a constant. So when we're integrating, an integral is a linear operator, we can pull out constants to the front of integrals. So we have a n times integral minus infinity to infinity of, now it's just psi n star psi n d tau. But we said also that this wave function is normalized, that psi n is normalized, and the integral of psi star n psi n over the entire domain of the wave function is just defined to be 1 if you have a normalized wave function. So this whole thing here, which is not the a sub n, is equal to 1 by definition. So what we're left with is just a n. So if we have a wave function which is an eigenfunction of an operator, then its expectation value just equals the eigenvalue for that operator. And we could even take this one step further. We can calculate the expectation value of that operator squared, which, if we know a certain property of operators, the operator A squared is just the operator A acting twice. So you should be able to work through this and see that instead of just getting one A sub n, we would act twice and get two A sub n's out, and so it would be A sub n squared. And you should be able to work through the algebra of that and see that. So then if we look at the uncertainty in the value of A that we measure, so the deviation, the variance of psi of A equals the difference between the expectation value of A squared minus the square of the expectation value of A, that subtle difference inside versus outside. And this is a an squared. And the second part is just the square of this, which is an, so that's also an squared. So that variance equals 0. And then the standard deviation, or uncertainty as we might refer to it, is just the square root of the variance. And so that is also 0 because it's just the square root of 0. So if we have an eigenfunction, not only is the expectation value the eigenvalue for that state, but the uncertainty in that is 0. So every single time you measure it, you're going to get that eigenvalue and only that eigenvalue. Now this is a special property just when we have psi being an eigenfunction here, where psi is an eigenfunction of that operator. And we'll look more later on about what happens when you have a wave function which is not an eigenfunction of the operator you're trying to calculate the expectation value for.